It's really my pleasure to give this talk to you this evening, and I would like to thank you for the kind invitation to give this presentation. So I will be speaking. I will give you an introduction on the application of optical spectroscopy for industrial application, and mostly I will focus on agri-food applications. Mohammed already introduced us a bit. So actually, I'm a professor at the university in Brussels, the B-PHOT Brussels Photonics Research Group. We led by
Lien, we cannot hear you. If you
can hear me now, Beck? Yes.
Yes, you're right. Yeah, okay.
Yes. So I first will give you a first short glimpse on our research group, and then I will go to the real talk. So actually, our photonics research group is led by Professor Hugo Tiempont, who you can see here in the center of the image. And as you see here, he's actually standing in front of our Photonics Innovation Center, which is a brand new photonics laboratory space. So actually our research group, it has two campuses. We have our key campus, our main campus in the center of Brussels, or close to the center of Brussels. And we actually built new laboratories outside of Brussels because there we had more space available, where we have our clean room facilities, our manufacturing facilities. So that's our Photonics Innovation Center. Now, in our research group, we are actually tackling different research topics. So we have two research lines that are really fundamental research and that are funded by the ERC, the European Research Council, and these are focusing on semiconductor lasers and photonic integrated circuits. And then we have also more research and innovation topics where we actually cover the whole supply chain, as you will see, considering freeform optics, optical fiber sensors, and biophotonics and spectroscopy, where I am working actually on the spectroscopy part and on the freeform optics parts, because here there are 5 distinct groups, but actually that's not really true in practice, because in practice our 5 groups are actually linked with each other, and the most interesting topics, let's say, are on the boundaries of different topics. So basically I am working on the edge between the spectroscopy and the optical design, and I'm trying to tackle the whole supply chain from spectroscopic research towards industrial integration of spectroscopy using advanced optical system design. So, optical spectroscopy and spectroscopy for industrial applications, I already highlighted it a bit. I'm especially focusing on food applications. And actually, I'm focusing on food applications along the whole food supply chain, on the field for crop growth, quality control, for food safety, for food quality, and also monitoring during the packaging and the storage. Now, if it's for food or if it has other purposes, the main thing that I want to achieve, my main challenge, is actually to identify products, to classify products, and to see what is the chemical composition of these products. And the main optical technique that I'm using for that is optical spectroscopy. Optical spectroscopy, for those who might not be familiar with that, just a very, very brief introduction. Actually, optical spectroscopy is a study where we study the light-matter interactions, and where based on these interactions, we get information on the chemical structure of our product under test. Now, if we start easy, let's consider just a bulky slab of material. If we illuminate a product, any bulky slab of material, a table, an apple even, a tomato, no matter what the product is, it can even also be glass windows or optical filters, every product will interact with our light. Most obviously, we will have part of the light that is absorbed, part of the light that is reflected, and part of the light that is transmitted. This might seem obvious, but actually is a huge simplification of what really happens. Because in fact, if we look to our products, much more interactions can occur. This can be the reflection of light, you having more a specular component or having diffuse reflection, also dependent on the surface roughness. It can be absorbed. Now, this absorbed light can just generate heat, but can actually also induce fluorescence light signals. And here we can consider just regular fluorescence, one photon-induced fluorescence, but we can also look to nonlinear fluorescence properties like two photon-induced fluorescence, where two incident photons will be absorbed simultaneously and give rise to an emittent fluorescence signal. We can have transmission of light, and we can actually have spatially resolved scattering, so where we have a partly transmission, but then still a reflection component of our light being present. Now, what we do in optical spectroscopy, we actually study for each of these interactions the light properties measured by the fluorescence intensity or the light intensity in general as function of the wavelength. So for fluorescence, for absorption or reflection, transmission of light, we can measure the intensity of the light as function of the wavelength. And this we can do in the visible region of the light, which actually will relate to the visual properties of our sample under test. But even more interestingly, we consider the UV region and the near-infrared wavelength region. And especially to focus on the chemical composition of products, the near-infrared region is really, really interesting. Now, what determines which wavelengths are so important and which wavelengths are the key characterizing wavelengths for a product under test? This is actually dependent on the molecular structure of our sample under test, because this molecular structure will determine the electron energy band diagram of our substance under test. Actually, if you look to our molecular structure of our sample, then you most probably know that it has a nucleus, and that around this nucleus you have electrons that are present. These electrons have certain energy levels in which they can be present, discrete energy levels, dependent on the molecular structure of your whole sample under test. So basically, if you look to the electron energy diagram, then you have different energy levels. And if we illuminate our sample under test with a certain energy, then our electron can actually undergo these electron transitions. For example, if we use visible light, and we have all colors of visible light present, and we illuminate, for example, a red substance, then basically all the colors will be absorbed and only a red one will be present. But in general, the energy that matches with the energy diagram or the energy gap here of our electrochemical structure will actually induce absorption of our incident light, and the other wavelength will just reflect or transmit through. As I indicate for a red apple, if you illuminate with all the wavelengths in the light, then actually all of them will get absorbed because of the electronic structure of our molecules, and only the red one will remain. And this is also inducing that we see this as a red apple. Now, as I indicated before, visible light, that's kind of obvious because we can see that also with our human eye, but we are more interested in other wavelength regions, the near-infrared wavelength region in particular, because also dependent on the wavelength that you consider, the wavelength of your incident light, you can stimulate different electron transitions of your molecular structure. Like if you go to the UV and visible light, you are within the electron transitions between the electronic levels. If you go to the infrared, you are working or you are playing on the molecular vibrations of your structure. Okay. Now, this might sound already really promising, like we have a technology that relates the light properties of light interaction with the chemical structure of our sample under test. Now, of course, we need to be able to measure that. We can, of course, illuminate our products under test, but also their stability of a source is really important. And then we need to, of course, observe the light. We need to measure this. And in the field, now this has been realized for using different technologies. Like, for example, you have camera systems. Think of multispectral, hyperspectral camera systems. You have spectrometers on itself. And then you also have these handheld systems going now more and more, for example, liquid testing, where you have compact detection units to be integrated with these sensors. Now, which technology fits best your application is actually dependent on the element that you want to sense, the complexity of the chemical structure, and the application. If whether you want to integrate it in a camera-based system or in a spectrometer-based system, and so on. So basically, for every application, for every sensing challenge, let's say, we go to a whole supply chain, going from a spectroscopic study, where we first try to identify the most suitable spectroscopic sensing techniques, the most suitable the detection principle, let's say. Then we combine it with advanced data processing, going from chemometrics to also machine learning, and then based on the most suitable identified hardware, so spectrometry device, let's say, and our optimized software processing, we optimize the illumination and detection towards an industrial integration and towards a prototype. And then, of course, we pursue validation in an industrial environment. Now, to actually cover this whole supply chain, we need to tackle different challenges. The first and one of the important ones is, of course, to identify the most suitable illumination and detection constraints. What are the wavelengths that are significant for our challenge that we want to solve? What is also need to tackle, of course, an accurate sampling of our product under test. And this is a real challenge for the food industry, because we have a lot of natural variation, differences between harvests, differences between the harvest in the US, in Africa, in Asia, different climates, different products. This is really significant and influencing our detection methodologies, while it is super important to have an accurate sampling of your whole product variability, because if you train, like, for example, a model with machine learning, you cannot assume the model will work on samples that it did not saw before. If you only train your model it's machine holy grail if it has been properly trained, and you cannot train your data with a limited data set and then assume that it will work for everything. It just doesn't work like that. So it's really, really important to combine an optimization from the hardware and on the software, and to actually have a full data set and reliable samples. So to actually give you a feeling of how this works, I will consider a few case studies, actually case studies along the whole photonics supply chain, just to give you a glimpse of what we have been doing in our group, but also that you get a feeling of how we tackle different problems. So I actually chose a few case studies along each of the food chain parts, let's say, so that you get a broad general overview. Okay, so first, crop growth. Crop growth, like for example, strawberry quality assessment. This is important in industry. For example, in these plucking robots, you can see one here. This was a project that we did together with Octinian, who is also a company having a large division in Belgium. And first, the plucking arm was just plucking all the strawberries. And what we actually integrated is a fiber inside of the arm that is illuminating the strawberry and that then is collecting the reflected light of the strawberry. So the illumination and detection are actually inside the robot, and it's guided to the plucking arm, to the plucking area here with the use of optical fibers. So what we first did was, of course, in the lab, we did a whole classification of different strawberries. We measured the reflection characteristic of a huge amount of strawberries, and then we related the spectral properties to the different strawberry classes. Following, we applied principal component analysis to actually define the most important, most striking parameters, and then we integrated it via the use of fiber optics. Another thing with respect to product quality evaluation can be the integration using cameras. Like, for example, on the field, and another application of on the field can be the use of cameras supplemented with a drone system, where we actually here do research on the integration of visible and near-infrared camera units and also short-wave infrared and thermal camera units. Why? Because if you have some smoke, like for example here with short-wave infrared, you can see through that. But also if you have a product, and this is the most interesting thing for us with short-wave infrared, this is really interesting to have for your product inspection. Why? If you have this apple that looks healthy and tasteful, let's say, in the regular image, then you see that with a short-wave infrared camera, you can see here a darker region. So most probably this apple fell down on these bruised parts, and with this you can immediately visualize this and see this. So therefore it's important to actually combine often different wavelengths, especially on the fields. On drones, you typically now have already the vegetation index monitoring, monitoring chlorophyll content, some quality parameters in the visible range, but also going to the shortwave infrared is advantageous for product monitoring. Shortwave infrared is also used for cellulose monitoring, for actually fire prevention. Like in Spain, in Italy, we often do fire prevention there on the fields using shortwave infrared. Same principle, actually, another camera, but also the concept of using different optical channels to actually evaluate the field. And here we do that with turf grass monitoring. So actually, if you have a football stadium, golf yard, these kind of environments, let's say, then we don't want to have our camera now on a drone, but we want to have one fixed camera mounted on lighting poles so that we can actually have an observation of the quality of the health of our field in one shot, let's say. Also here, just one regular camera is insufficient, but we consider a 5-channel camera system, 1 thermal channel in the center, and then 4 visible near-infrared channels, all with different spectroscopic filters, spectroscopic bandwidths, so that we can monitor as much as possible vegetation indices at once. And then, of course, these 5 images are processed using machine learning algorithms to actually get all these vegetation indices out of it to actually monitor the vegetation health. This system was not only optimized for vegetation health, but also was monitoring the need for pesticides and the irrigation needs, such that we could optimize the use of resources and actually go to sustainable maintenance of our turf grass area, which is really, really important at this moment, because you know that we are facing climate change. We cannot change that anymore. anymore, let's say. We need to learn to live with that. I don't know the situation in Egypt, but in Belgium, every year we see that we get longer periods of drought, that we really need to start thinking about our irrigation techniques. Also, the use of pesticides is becoming more and more important and more regulated by the European Commission as well. So going to the monitoring of all these parameters to enhance sustainable maintenance, sustainable agriculture is really important. Another project was for the monitoring of microplastics, where here we go to a more handheld compact system. So you actually can see a test liquid flowing through the chip over here. And what we do here is actually we illuminate this area. We also look to the detected area, and we want to identify microplastics in the water with that. I don't have results yet on this. It's just to give you the general concept, because this is actually a project which is currently running at our department, but which will give a very compact sensing. So then we can go to quality control. Quality control, this can be really everything related to food and the food chain. It can be the detection of foreign objects like pieces of glass, pieces of metal, animals that get into your food chain. It can be the detection of toxins into our food, like the mycotoxins, which are really, really harmful for our health, are invisible for the human eye, and can be formed on the field and during storage of the products. So they really are one of the main causes that food is rejected and withdrawn from the food chain at this moment. Acrylamide is an important toxin as well that forms during high temperature processing of starch-rich food products. And then we have water quality, as I indicated before. And then we have olive oils, honey, and then for Belgium, it's also beers, because there is fraud with Belgian beers. Not all Belgian beers that you can buy appear to be real Belgian beers. So there is these products are really, really sensitive to fraud, and therefore it's important to identify the real authentic one and the fake one. So we do that by UV-Vis near-infrared broadband spectroscopy, where we actually, dependent on the products, we have different setups available in the lab, able to study the broadband spectrum and then to combine it with chemometry and machine learning. Considering the reflection spectroscopy, we typically work with these the products and then to collect all reflected or all transmitted light, which is very useful to have an absolute measurement of the reflected and transmitted light. We also have fluorescence spectroscopy, which is, for example, particularly interesting for mycotoxin and aflatoxin detection in particular, where we can, for example, use a laser setup to determine the localized aflatoxin presence in maize kernels. You can see here on the top left a healthy kernel, but then on the right you see a local contaminated part of the kernel. The bottom left is a more or less homogeneously contaminated kernel, and then on the bottom right you see a contamination on the edge. So basically, we first optimized here the excitation wavelength, excitation power, power density as well. And then we studied the fluorescence properties of our products, of the healthy products and of the contaminated products. Because actually one of our key observations is that for the toxins to actually enhance your limit of detection, we are not longer measuring the toxin fluorescence itself, but mainly the influence of the toxin fluorescence on the natural fluorescence of the food products. Because food products have a lot of fluorescence backgrounds that they emit because of the proteins that are present, because of pigments that might be present. So basically, this huge fluorescence signal of natural products, healthy products, we measure the influence of the toxin presence on these backgrounds. We study both one-photon-induced fluorescence, so where one photon of our incident light is absorbed and gives rise to a fluorescent photon, and we study two-photon-induced fluorescence, where two incident photons are simultaneously absorbed, and give rise to the fluorescent emission. The fluorescent emission is, in terms of the wavelengths and in the energy, more or less the same, because the same band gap is present. However, we see that the contrast between the healthy samples and the contaminated samples is larger for two-photon-induced fluorescence than for one-photon-induced fluorescence. Because for one-photon-induced fluorescence, you see that between the healthy and the contaminated samples, we see mainly a wavelength shift, while for the two-photon-induced fluorescence, there is a wavelength shift, but there is also the intensity that is significantly different, which is less the case for one-photon-induced fluorescence. Typically, what we do here as a first processing is we consider ratios of fluorescence signals, where we actually try to cloud our data to generate these clouds and to come up with a detection criterion to be able to differentiate. And then if we found good fluorescence intensities, the most optimal ratios, then these wavelengths are considered in the next step in the machine learning processing, where we actually try to avoid to work with the whole spectrum to limit the processing time. And why do we want to limit the processing time? This is actually because one of our key applications is to use fluorescence spectroscopy into these food sorting machines, where actually the food products are scanned at really high speeds, where the unwanted products are really rapidly identified, let's say, and the unwanted ones are blown out of the food stream with just a burst of air. So therefore, we cannot afford to use machine learning on the full spectrum, but we first identify the most interesting wavelengths, and then we consider this in further processing. Integration in food sorting machines is, of course, one industrial application. Another one is the integration in handheld devices, where, for example, we work together with Goya Lab to integrate this aflatoxin sensing into a handheld spectrometer, and where first test of this spectrometer actually showed a really good differentiation between the different contaminations. A final food safety point is the acrylamide monitoring. Acrylamide, which is a carcinogenic substance that forms at high temperature processing of, for example, potatoes. So actually, I'm from Belgium. So one of the key problems in Belgium is the acrylamide formation during French fries production. Because actually, these top and bottom French fries, you would not say so, but they were actually resulting products when applying the same frying conditions. So I applied the same frying temperature, the same frying time, but the bottom one originated from potatoes that are unsuitable for frying, so that actually generates too much acrylamide during the frying process, while the top one, these are of course the favorable French fries that we want to have. In the Belgian French fry industry, let's say, at this moment in the big companies, they do a color sorting on the fried French fries to the first fried ones, because in Belgium we fry our French fries 2 times, but I will leave that aside to avoid complexity. So basically in the big companies, what they do is they fry the French fries and then they apply color sorting. And all the French fries that appear too brown because of the acrylamide formation are filtered out. Now this induces huge food losses. Because if every time the French fry is too dark and you need to actually throw it away, this is unnecessary food loss, which we don't want to have. So basically what we wanted to do is we wanted to come up with a solution that can monitor non-destructively the raw potatoes, measure the acrylamide precursors, being starch, reducing sugars, water, or asparagine, and relate these acrylamide precursors to the acrylamide formation after frying. So that actually based on a measurement of the raw potatoes, we can estimate if the potato is suitable or unsuitable for frying, meaning that then the unsuitable potatoes would still be able to be used for low temperature processing, like in mashed potatoes, potato soup, and so on, minimizing food losses. And we did not just wanted to do that, we also wanted to comply to the European limitation, who actually set a legal limit on the acrylamide presence in our food. And you see in 2020, it's now a few years ago, but it are the most recent numbers that are available. This was still a highly technique that was highly required, because then there was still way too much acrylamide in our food. Now, to measure starch, reducing sugar, water, and asparagine at once, we actually focused on the light scattering, combining internal scattered light and specular reflection of the light. Because actually starch, water, it will influence the firmness of the potato, so it will influence the specular and the scattered light. To give you an idea of what we measure, it's actually the glow which you see here. So you have here the bright white spot. This is your incident light. And then you have a glow around it, like you don't have it with the stone because it's much harder. But here in the potato, you can see like the internally scattering of your light a little bit with the glow. And this is actually the glow that we want to study here. So therefore, to be able to study this glow, we in-house developed a measurement setup comprising a supercontinuum source to illuminate our potato, and then a detection arm, which is actually scanning our potato and is measuring measuring the specular reflection and the internally scattered light, but it's measuring it on each area of your potato. So it's collecting the light at different positions of the potato surface. And using this technique, we can actually measure the specular reflection, the scattered light. That's also why we have a supercontinuum source, to have actually a good signal-to-noise ratio of our scattered light. And we are then able to actually see a relationship between the light scattering, as you can see here, and the acrylamide precursor concentration that is present. So in this solution, we can then actually come up with different ring sensors to measure these acrylamide precursor concentrations. Now here, I was mainly speaking about spectrometers itself. Of course, having a spectrometer enables you to have an accurate spectral representation. You can also do that using spectral cameras. The reason why we don't use spectral cameras into our lab is because our spectrometers are flexible. We can adapt the spectral range easily. We have different configurations, but also we can really adapt the spectral resolution and the integration time that we can have with our spectrometers, while with hyperspectral multispectral cameras, the tunability is less. So we go to cameras, but actually only after a pre-study using spectrometers to determine the most crucial parameters, like which spectral resolution do we require, what is our dynamic range that we need, and after we have a good identification and characterization of our measurement constraints, then we might look for a spectral camera fulfilling these needs. So then the last examples are actually on packaging and storage of foods. One is, for example, the inspection of food packages, so the seals, where we, for example, applied also near-infrared spectroscopy to identify, for example, cheese in the sealing of cheese packages. You can see in the visible wavelength range, so just with the human eye, let's say, you would not be able to see the cheese within the food package sealing. So even if you would have people inspecting the cheese package, you would not actually see the presence of the cheese because also of the colors that are present, of the plastic that is used, you can just not look through it. While if you consider near-infrared light and you actually measure the near-infrared spectrum, you see that the cheese has a significant near-infrared absorption feature, enabling to differentiate the cheese from the sealing plastic. So even if we cannot see it with our human eye, a near-infrared camera is able to see the cheese in the sealing. A similar example, or actually also an example for storage, is the wine aging in wine barrels. Wine is stored in wine barrels, and this is a kind of important procedure because actually part of the taste of the wine comes from the barrel. In the barrel itself, there are components being present that give off taste to the wine, and then the taste becomes more powerful and more tasteful. Now, of course, if you put in the wine in the barrel, the barrel has a lot of these components, but of course it dissipates to the wine, and then the wine is bottled, and you don't know how many of these taste-making components, let's say, are still present in the barrel. So actually now, a lot of barrels are perhaps thrown away while it's not really necessary. And wine tasting is important for that, but it's not really an objective way, let's say. So we integrated different optical fiber sensors, which are actually kind of reflection probes that monitor the components into the barrel. So actually at different thicknesses of your barrel, there are the fibers present, and they see how much of the components are already dissipated into the wine, and they can actually predict the wine taste without having to taste the wine itself. I until now give all the examples or that I wanted to give you about the detection itself. Now there is one crucial thing that I didn't mention, and this is the illumination. And illumination is so important because you can have a brilliant spectrometer or a brilliant camera, but if you don't use a proper suitable illumination, actually your detector will not measure anything. Without good illumination, there is just nothing. And this is an important message that I want to give, because if you look to all the sensing publications currently, they're all about the sensors, about the multispectral cameras, the hyperspectral, about the spectrometer, about the machine learning on the data. And I believe they often forget the illumination, because if you don't have a perfect homogeneous illumination, if you don't have an illumination source with all the wavelengths being present that you want to study, then basically you will never get good data either. So therefore, just a remark on the importance of illumination. It's important for spectroscopy, but also for, like, for example, the greenhouse lighting. Because if you fine-tune your illumination in, for example, greenhouses, you can not only boost the plant's needs, the plant growth, because you can optimize the spectrum towards the absorption spectrum of the plants, but you can actually also integrate some spectral sensing on it. Like if you have a greenhouse and you have optimization of the lighting that is there, you can actually also measure reflectances, and you can also get some spectral information out of that and get information about the situation in the greenhouse. Also, another important illumination is now the UV illumination. UV for disinfectation. It became popular with the COVID crisis. It doesn't work always, or it depends on which level of disinfection you would like to have. But also UV labels or UV sensitive labels are used for product storage monitoring. Like you might have heard about labels that they put into the temperature, quality levels. And then, of course, I indicated the food sorting machines, which are scanning machines, but also illumination for like these labeling or to put the labels on the wine corks, let's say, is also something that is now emerging, let's say, also within Industry 4.0. A lot of laser scanning systems are currently used for laser marking, laser engraving solutions. So with this, I came to the conclusion. I hope in this presentation I was able to explain you a bit of the potential of optical spectroscopy for the photonics sensors. I particularly give some examples in the agri-food industry because that's the industry in which I'm working. But actually, optical spectroscopy is really powerful. It gives you insight in the components that are present into your sample under test. And if you consider spectroscopic sensing systems just in general, then it really requires optimization of the illumination of the detector, of the data processing, and it actually touches onto a lot of different photonics subfields, let's say, that need to work together to optimize really your sensing performance. And with this, I would like to thank you for your attention.